So here we have the dendritic pattern. So you see this kind of vein type structure all leading. So here it looks like, from what I can tell in this picture, this looks like some sort of shale or soft sand in this region here, but it's probably relatively flat lying. It's not folded, right? So it's a uniform or a homogeneous bedrock. Now, the next one here, we have drainage going out in all directions. So if we look at a topographic map, we would know that there's a hill or a volcano here, radial pattern. And then here we have the rectangular pattern. So here we have two parallel streams, and they should be joining at right angles. So we see that they're probably joining down over here, but you can see sort of this one joining at right angles right in here. There'll be these steps here, 90-degree angles right in here, usually because of some joint pattern. And then for the folded strata, the trellis, so here we can see there's some sort of tilted monocline or some sort of beds. Here I actually see a syncline and an anticline here, and so we have the more resistant sandstone beds here, and then they separate the weaker shale where the streams occur. And here we see that the streams are joining some trunk stream, some main stream that goes in here. So here would be the main trunk stream, and these little streams eventually join up with those main streams there. And then finally, the last one are these parallel drainages, where you have this uniform slope, and you can see there's a series of streams all leading to this main trunk stream right in here. Another topic I want to mention here is your book at the beginning of the chapter does talk about this process of headward erosion. And so here we have a higher plateau, higher region, and we see that as drainage occurs here, it develops into these creeks here that goes to the lower lands over here. So here's a main stream coming through here. But as more precipitation occurs, you're going to get this process of headward erosion, where as a river cuts into its channel, down cutting, it's going to cut and cause the erosion to occur upstream, up into its drainage basin. So that's what we call by headward erosion. Eventually the stream will downcut, and this drainage basin will get larger and larger and start growing farther out and increase basically in sizing or eroding more into this plateau. In that concept of headward erosion, there's a process where one drainage basin, one stream, can capture the waters of a different drainage basin. So we call that stream piracy. So in this case, headward erosion will cause erosion to occur into the divide and expand the drainage basin of this creek here. As headward erosion continues, you can see it's going to cut through this divide and will capture the waters from this stream, and this becomes the point where we see stream piracy. This is common in many cases, usually where the divide is composed of softer rock. There's a concept of a permanent stream versus a ephemeral stream. So a permanent stream is one that exists throughout the year. It's fed by groundwater during the dry season, and it's obviously fed by rains during the wet season. For the ephemeral stream, it only has running water in it during the wet season, and in the dry season, the water table drops below the stream bed, so no water is fed into the stream. In fact, let's get a couple of pictures here. So here's an example of a permanent stream that's perennial, that exists throughout the year. You can see that the water, the groundwater is continuously feeding this stream even during the dry season. And for an ephemeral stream, here you can see the water table is below the stream bed and it's not getting fed any water. There's a term that your text doesn't really mention, but it's mentioned here in the PowerPoint, and there might even be a quiz question on it. But there's this place called the hyporheic zone, and it's a zone where there's a pressure difference or pressure gradient between groundwater and the water that's percolating through the stream bed. And so during dry seasons, obviously there'll be more pressure from the groundwater, so you'll be feeding water into the stream. When the river gets larger, or if it gets into flood stage, this zone would be different. Well, there'll be more pressure from the stream, and then to be feeding the groundwater. So it's a balance that occurs here. But when we look at perennial streams during dry seasons, they're getting their water from the groundwater. So earlier we talked about this concept of discharge. And discharge, again, is going to be our volume of water passing through a cross-section of the stream in a given unit of time. And so the volume of water is going to be measured in cubic feet or cubic meters. And so you've probably heard of the term CFS for cubic feet per second. So cubic feet per second. So it's really a volume of water passing a fixed point through the river, a cross-section through the river in a unit of time, in this case a second. So if we have a river, so let's say the river is about 8 feet wide, the depth is about 2 feet, and the velocity is about 1.5 feet per second. So the discharge will be the width times the depth times the velocity, right? So remember, these two are basically the area. Those two make up the area, and you have to measure those, and then we have to have some sort of flow meter to measure how fast the water is moving. And so if you do the math here, a stream with those dimensions and the water moving at that velocity would be 24 feet per second, right? Because you have the width times the depth and then times feet per second. So that gives us our cubic feet per second. So there's our volume. So discharge is how we're going to measure how much water is coming down the stream. Discharge reflects the size of the drainage basin and climate. Obviously, in wetter climates, you're going to see more discharge. And the size of the drainage basin, obviously, like I mentioned earlier, at the headwaters of rivers, you have usually lower discharge. But as you move downstream, you'll see greater discharge because there are tributaries that are contributing to the river. Now, let's look at some examples. The Amazon River, I showed you an image of its drainage basin. It's an enormous drainage basin. It's 15% of total runoff on Earth, and its discharge is 200,000 cubic meters per second. Well, that's over 7 million cubic feet per second. That's incredible. It's hard to imagine how much water is that really means. And just to compare it, the mighty Mississippi River, and I showed you that drainage basin as well. Well, that's 17,000 cubic meters per second. Well, equates to 600,000. So it's nowhere near the size of the Amazon River. So the Amazon River is really an enormous drainage basin. And just for comparison, I was looking at some data for the American River here in California that drains from the Sierra Nevada. And even at flood stage, we're seeing 166,000 cubic feet per second, which is about 4,700 cubic meters per second. So that's a huge amount of water. But again, it's nothing compared to what we see in the Amazon River. So thinking about discharge again, in temperate regions where we see more rainfall, discharge increases downstream because there are tributaries that add more water to the river. But in arid regions, there may be some discharge near the headwaters, but discharge will either decrease or completely go away because of evaporation or groundwater infiltration, because the water table is so low, and so those rivers just become dry. So drainage varies with time. So obviously you see more discharge in the wet season, less discharge in the dry season. The next topic deals with stream erosion, and there are a variety of factors. Remember, gravitational energy makes running water move, and 3% of that gravitational potential energy goes into the work of eroding the stream channel. And it does it in 4 ways. The first way is scouring, and you're removing loose sediment by the running water, just scouring, picking up loose sediment that hasn't been lithified. Or we can break and lift. So this would be lithified rock where hydraulic pressure, hydraulic action can break chunks of solid rock off the bed or the banks of the river. We could also see abrasion. Remember, the sediment is carrying load, and the load could be in silt or sand, and that could act as sandpaper that'll abrade and weather some of the stream beds and stream banks. And so we get this process called making potholes or flute marks or fluting, which can occur as well. So here are some potholes. So what happens is you can see the creek, which is down over here, the stream, but when there's higher discharge, higher water levels, we'll get stones or pebbles that will get caught on here, and this eddy will cause swirling that goes around in here, and literally these things literally get drilled by this abrasive action here. This next picture is showing a field trip I took with some students out to the Owens Valley in the eastern Sierra Nevada. And this is a now dry river called the Owens River. But during the last ice age, there was a lot of snow melt, glacier melt that came down through these valleys. And what happens is, as the water was moving, you can see that the silt in the water was abrading and polishing these rocks here, right? So that's what we call fluting. So these are the flute marks. There's also some potholes that are developing. So these waterfalls will cascade down into this gorge here. Oh, beautiful flute marks right in here. So that's what I mean by fluting there. And finally, the last type of stream erosion is dissolution, right? Water is a universal solvent. It dissolves just about anything. I mentioned a little bit about load. So sediment carried by the stream, and there are three types of load. Dissolve load, right? So I usually call those ions in solution. They'll either be positive charges or negative charges. And eventually these dissolved components, calcium, carbonate, potassium, they'll precipitate as chemical rocks like evaporites, right? And then there's also a suspended load. So this is usually mud size, silt or clay. And it's so fine grained, it's always, as long as the water is moving, this will always be suspended in the water column. It's what makes most rivers chocolate brown, the suspended load. Then bed load is usually the sand and gravel. And it's always in contact with the bed. And so it's going to move in three ways. So this bed load moves in three ways. It's either going to move by rolling. So some of the bigger particles, especially the cobbles, will roll down the stream. There'll be some sliding. Some of the flat clasts or broken particles will slide down. Or saltation. Saltation involves the bouncing, usually of pebbles or sand grains, right? So they're always in contact with the bed, even though they're suspended for a short while, but they'll come back down and bounce. So three ways of bed load movement. Couple of terms here. The competence of a stream is, well, how big of a particle can it carry? Can it just carry pebbles, sand, or silt, or can it move big boulders? Usually, the ability of a stream to carry huge boulders would be during flood stage when there's more energy. So remember, more water, more velocity, more energy. So actually, I wouldn't say flood stage. I would say more that it's occurring when there's a higher discharge. Because once flood stage occurs, actually the energy drops, and you won't carry those boulders, because the water will leave its channel. And when the water leaves its channel, it's not channelized anymore, so it slows down. It spreads over a wider region, and it'll drop the load. And that's what happens during flooding. That's why after a flood, when the flood waters recede, you just get this blanket of mud everywhere, because all that load was dropped off when the energy of the river decreased, because it left its banks, left the channel. Now, the other concept here is stream capacity, and it's the total quantity of sediment of a stream can carry. So how much load can it carry? Obviously, larger rivers like the Mississippi and the Amazon can carry more capacity. Some other terms here, alluvium. Alluvium is sediment transported and deposited by streams. And fluvial refers to stream processes, anything dealing with streams. So there are terms called fluvial deposits. Well, fluvial deposits are just alluvium. So that's really the same thing, alluvium and fluvial deposits. And they depend on the decrease in flow velocity. So remember, think about that river in its channel has more energy, so it can move more load. But when it floods, it leaves the channel and it drops that load. So if there's a decrease in flow velocity, if it's a small decrease, then only larger clasts will settle out. So those are the bigger, the gravel, maybe sand will settle out. But if you see a big decrease, like in the flood stage where the river leaves its channel, then even the clay and silt will settle.